Hello everyone and welcome to my thesis defense. I'm Juuso Eronen and today I would like to present to you my research in improving multilingual automatic cyberbullying detection with feature density and zero-shot cross-lingual transfer. In this presentation, I will first give an overview of cyberbullying detection research and then introduce the two methods for its improvement: classifier performance estimation with feature density and cross-lingual transfer using linguistic similarity. The contributions of this work are as follows. I propose feature density, a measure to roughly estimate classifier performance and to reduce the number of required experiment iterations. This is important as in order to train a good model, one has to run lots of experiments which take both time and consume notably large amounts of electricity. I also propose to use linguistic preprocessings to improve machine learning classifier performance. I apply zero-shot cross-lingual transfer to cyberbullying detection. I demonstrate the potential of zero-shot cross-lingual transfer also for other natural language processing tasks. And lastly, I propose using linguistic similarity for optimal transfer language selection. This is important as by using transfer learning, it is possible to develop models for languages lacking data without the urgent need to go through the costly process of collecting and annotating the required datasets. Let's start with the cyberbullying detection overview. This research helps in dealing with problems found in forums, social networking services, and other means of online communication, specifically cyberbullying, which has become a major problem in the previous years. Cyberbullying includes, for example, online harassment, humiliation, ridiculing someone's appearance, personality, etc., spreading rumors or slandering, or discrimination. The damages this kind of behavior can cause are also very serious, including alienation, aggression, depression, self-mutilation, and in the worst case, suicide. Here are some main characteristics of cyberbullying and how it differs from traditional bullying. It is easy for the bullies to hide behind the anonymity of the internet as there is no need to show your face. Also, the bullies can't see what their actions are doing to the victims, so they tend to lose their inhibitions and don't think about any consequences for their actions. Also, a couple of bullies can cause a snowballing effect, leading to more and more bullies to join. What makes this situation even worse is that the victim basically cannot run from the bullies, as going online means you can be targeted. There have been attempts in forming internet patrols to manually check messaging boards and social media to detect cyberbullying. But this requires too much time and effort, and it's also a psychological burden for the patrol members. So the solution is to automatize the detection using artificial intelligence. The main goal of automatic cyberbullying detection is to create a detection tool based on artificial intelligence to reduce the human effort needed in prevention of cyberbullying. The research has mostly been done in Japanese, English, Hindi, Arabic, and Polish, and the classification methods have improved throughout the years from simple methods like support vector machines to deep learning, and most recently to using transformer models. Also, different feature selection methods have shown great potential for a task. These have improved from using bag of words to word patterns and to using different kinds of linguistic information. Also, the importance of expert annotations and proper annotation guidelines have been shown for the task. One of the biggest challenges in the field of cyberbullying detection is the urgency of the problem. The victimization rates of cyberbullying are constantly increasing due to the integration of social networking services to our daily lives. This calls for the need to develop the detection systems as fast and as efficiently as possible. However, this is being held back due to the increases in computational costs in creating models and the costs in creating datasets. Also, it is especially important for cyberbullying datasets to be annotated properly using experts due to the complexity of the problem. The abusive content could be hidden, for example, in supposed humor or sarcasm. Additionally, the detection models should avoid becoming black boxes due to the contentious nature of online content moderation and its intersection with the issues of censorship, free speech, and privacy. In order to make it possible to detect cyberbullying as early and as effectively as possible and to prevent its serious consequences, the purpose of this research is to hasten model development by reducing computational costs and to enable the development of detection systems even when lacking data. First, I propose to use feature density to estimate classifier performance prior to training and to reduce the number of required experiment iterations. There are many classifiers and feature sets that need to be considered when developing harmful and abusive behavior detection methods. This is both time-consuming and computationally intensive. Also, in the recent years, the computations required for building models has greatly increased, and this also comes with a significant carbon footprint. Also, there are huge amounts of social networking services and multiple languages, all of which need their own systems. These problems are further worsened by the popularity of deep learning and the increases in dataset sizes. One could say that the total effort needed to develop these systems comes from the number of classifiers times feature sets times social networking platforms times languages. Here, I concentrate on the classifiers and feature sets, while in the next part I concentrate on the languages. In this study, I want to know how feature density can be used to estimate classifier performance and to reduce the number of required experiment iterations, and which classifiers work with which feature sets and yield the best results. My proposal is based on lexical density, which is my proposal is based on feature density, which is an extension of lexical density, and instead of using the number of words, I use the number of features obtained by applying different kinds of linguistic preprocessings. And previous research suggested that feature density could correlate with classifier performance, at least for Japanese data, as a positive correlation was found for convolutional neural networks and a negative correlation for other classifiers. This means that it could be possible, it could be useful in estimating how the data should be preprocessed in order to find the optimal point of performance. This would allow for more efficient model development. The applied dataset is from Formspring, a former social networking service that was infamous for its cyberbullying issues. The dataset was originally annotated using Mechanical Turk, but as these annotators had no expertise in cyberbullying detection, the dataset needed to be re-annotated with trained experts. The dataset contains almost 13,000 samples, of which a little less than 1,000 were harmful, meaning cyberbullying. I applied different kinds of linguistic preprocessings in order to change the feature density of the dataset. These methods include tokenization, lemmatization, parts of speech, named entity recognition, dependency structures, chunking, stop-word filtering, and filtering of non-alphabetic characters. I produced a total of 68 datasets by combining these different preprocessing methods, with some of them adding information and some generalizing the dataset. This resulted in a wide range of different feature densities. And here's a table showing all of the 68 feature sets, and these are the possible combinations that can be formed using the proposed methods. The following classifiers were trained and evaluated on all of the previously mentioned preprocessing methods. These classifiers include both simple methods and some neural network classifiers. Here are the classifier results. Support vector machines, multilayer perceptron, and logistic regressions performed the best, while convolutional neural networks' performance was below average. It is notable that most of the top scores were obtained with other feature sets than tokens. However, using pure tokens was still among one of the highest performing preprocessings overall, which explains their popularity. Also, most classifiers show a negative correlation with feature density, and there was no correlation with convolutional neural networks. I found out that extremely low feature densities, for example, using only parts of speech tags, were not viable with any of the classifiers, as too much information is lost in the preprocessing. Simple classifiers, like support vector machines, also could not process very high feature densities like those of dependencies. The dependencies and their variants still performed well with convolutional neural networks, and this shows the network's ability to assemble more complex patterns from tokens and relations that are otherwise unusable by other classifiers. So for most classifiers, there seems to be no need to consider very low or high feature density feature sets, and the best performing feature sets were found within 0.05 to 0.15 feature density, which is around plus minus 50% from the base density or the feature density of tokens, which is indicated by the thick line. This range includes 38 out of total 68 preprocessing methods. Adding part-of-speech information either to the corresponding words or as separate features often increase performance. Generalizing the data with stop-word filtering had positive results most of the time. However, other generalization methods did not work so well, showing even negative results in some cases. Furthermore, all kinds of generalization had a negative effect on convolutional neural networks, which further shows them from benefiting from more complex patterns. So most classifiers got an improvement over using tokens, and convolutional neural networks performance improved exceptionally well. To verify these results and to be able to develop a method applying the concept, I also ran the experiments on expert annotated Japanese and Polish cyberbullying datasets. The results were mostly similar to English, and the best classifiers were support vector machines, logistic regression, multilevel dissertation, and convolutional neural networks. However, lemmas were better than tokens for both Polish and Japanese, possibly due to them being more morphologically rich languages. Supplementary parts-of-speech tagging worked well, while stop-word filtering did not work for Japanese. Also, the best scores were in a similar range of feature density for all of the languages. And here you can see the top scores being in a similar range, like around plus minus 50% from the base density for all of the three languages. Also, I wanted to verify the results on a dataset of a different domain, sentiment analysis, in order to confirm the method's applicability to other tasks. Sentiment analysis aims to identify the emotional tone of content most commonly between positive and negative. The task tends to be easier compared to cyberbul detection, as the focus is often on specific keywords instead of more complex patterns. I used the Yelp Reviews sentiment analysis dataset, which contains reviews of businesses in North America. It has almost 7 million samples rated from 1 to 5 stars, of which I took a subsample of 500,000. 250,000 were positive and 250,000 negative. I ran the experiments also on this dataset. However, the supplementary preprocessing did not work so well. The classifiers already got very high scores with the base feature density or with tokens, and the scores were similarly high across all feature densities. And this is probably close to the maximum achievable score on the dataset. The reason why this happened is probably due to that I binarized the rating scale by only taking 1 and 5 star reviews, which make the learning problem way too simple compared to cyberbullying detection. In order to determine the best feature sets, it is needed to find the high-performing classifier preprocessing pairs that are also stable, meaning that their performance should have as low variance as possible within the cross-validation folds. I hypothesized that the well-performing stable classifier preprocessing pairs would be similar across datasets, and that the highest performance would be found in a similar range of feature density. The most stable feature sets for English were tokens and lemmas with parts of speech and or added stop-word filtering. And the highest score was with using parts of speech, tokens with parts of speech and stop-word filtering. For Japanese, the results were similar, but lemmas performed slightly better overall than tokens, and the best score was with using lemmas with parts of speech and stop-word filtering. The top scoring feature set for English was ranked 9th in the case of the Japanese dataset. So it could be said that tokens and lemmas with parts of speech and stop word filtering could be the best and most stable feature sets, and these include 12 out of the total 68 proposed preprocessing methods. And here are the 12 best feature sets highlighted. I tested this on the Polish dataset. To confirm the hypothesis, the best performance should also be found in the same range for this dataset. And instead of running the experiments on all of the feature sets, I run only the 12 best sets found previously and then searched near the feature density of the highest score if not satisfied. At the start, I had an F-score of 0.456 with the base feature density, and next I ran the 12 best feature sets found earlier and the score improved to 0.5 using lemmas and stop words. If the score is too low, it is possible to search for a higher score near the feature density of the current top scoring one, but in this case the score is already at its maximum obtainable with the proposed feature sets confirming the hypothesis. So one could have just stayed at the previous score to save resources as the score already improved a lot, but it is not possible to know beforehand what the score would be. The method seems effective for cyberbullying, but not for sentiment analysis, probably due to the simplicity of the task. Also, an important thing to note here is that lemmas work better for both Japanese and Polish, whereas tokens work better for English. This is probably due to Japanese and Polish being more morphologically rich languages. For them, the token feature density is too high for classifiers to optimally generalize on. Lemmatizing lowers the feature density, decreasing the dataset complexity and thus increasing the score. To train the models, I used an NVIDIA GTX 1080 Ti GPU for the neural classifiers and an Intel i9 processor for others. And here you can see the power consumption for support vector machines and convolutional neural networks. And the thing to note here is that the support vector machine model is much less resource intensive to train compared to the convolutional neural network. Applying the method saves up to 80% of the required training time when using 12 out of the 68 preprocessing methods. And in this case, it means around 30 to 60 watt hours when training a support vector machine model, and up to 20,000 to 50,000 watt hours when training a convolutional neural network. This roughly equals driving a car for 50 to 100 kilometers in emissions. So the method can both reduce the training time and emissions, which is especially important for neural networks. The method also comes with a significant performance improvement, as the F-score improved drastically on the Polish dataset with just 12 runs. There is also no need to consider all of the possible feature sets and classifiers. Additionally, I fine-tuned a state-of-the-art language model, Roberta, on the English dataset, and this showed an F-score of 0.797, which is actually slightly lower than the highest score by support vector machines. And this shows that simple models can achieve similar performance to state-of-the-art models with proper preparations. The reason why I didn't consider this model in the first place is that it simply wasn't released at the time. Next, I propose to use cross-lingual transfer in order to aid the development of detection models when lacking data. One of the biggest challenges in natural language processing is related to the availability of data. This means that in order to successfully train models for all of the world's languages, one would need to annotate a dataset for each language. This is a very difficult and costly task and has led to a small number of high-resource languages to dominate the field, most notably English. This imbalance in the distribution of resources among languages calls for the need to develop solutions that would aid in model development for languages lacking data. As I said before, the total effort required to build the detection systems comes from the number of classifiers times feature sets times social networking platforms times languages. And here I concentrate on the languages. Previously, I demonstrated how to hasten model development when a proper dataset is available. In this study, however, I want to know how to deal with the problem of cyberbullying in a language that has no available training data. The concept of transfer learning allows for model training with a language different from the target language. So the solution is to leverage knowledge from other languages. However, simple models like those used in the previous experiments with feature density are incapable of this. But it is possible by using a large multilingual transformer model thanks to contextual word embeddings. Furthermore, using zero-shot learning does not require any labeled data in the target language, meaning that the model is trained completely by using labeled data from another language. This can also be used as a temporary solution to train models for low-resource languages. Previous research showed that it is possible to achieve good results using cross-lingual transfer also for abusive language detection, and that transferring between more similar languages could yield higher scores. But the question is how to find an optimal transfer language. The current methods are mainly based on the individual's own judgment, field experience, and accumulated theoretical knowledge, or by simply defaulting to English. The current methods have many problems as they are prone to bias from the practitioner. In fact, one could say that there is no systematic method that could be used to determine which languages should be used as the cross-lingual transfer source. The hypothesis was that cross-lingual transfer performance would correlate with the similarity of the used languages, meaning that the more similar the languages are, the higher the performance would be. Recently, pre-trained transformer models have become the cutting-edge standard for many natural language processing applications. These models use an attention mechanism to learn contextual relations between words in a text, allowing them to also capture semantic meaning. Examples of these models include BERT and Roberta. The models are pre-trained on huge datasets, for example, on Wikipedia in an unsupervised manner. Also, training the same model on multiple languages causes the contextual word embeddings to align between languages, allowing for cross-lingual transfer learning. The models used in this study include two massive multilingual transformer models. XLM Roberta, which is basically a Roberta model trained on 100 languages. It has achieved state-of-the-art results in a variety of cross-lingual benchmarks. At Multilingual BERT, which is a multilingual version of BERT, and while outperformed by XLM Roberta in most tasks, it still showed some cross-lingual capabilities and achieved a good performance in various zero-shot transfer tasks. So how to measure the similarity of languages? I did this by using multiple linguistic similarity metrics based on linguistic features. First, EasyGlot, which is based on lexical similarity. eLinguistics, which is based on phonetics. It uses a predefined list of words to check for similarities between the usage, in the usage of consonants between languages. And lastly, I quantified the World Atlas of Language Structures, which is a database of phonological, word semantic, and grammatical knowledge of languages into a linguistic similarity metric. EasyGlot simply makes use of lexical similarity, which means using the number of words shared between two languages. eLinguistics is based on comparing phonetic consonants on a predefined list of words, and here is an example with English and German. If the consonants match, the similarity is high. If they don't match, it's low. The weakness of this metric can also be shown here as, even though both I and Auge originate from the same Proto-Germanic word Augo, the similarity between them is 0 due to not sharing any consonants. The metric quantified from WAS, on the other hand, is based on over 200 different linguistic features from multiple domains compared to only using a single feature like the other metrics. As WAS is just a database of linguistic information, I needed to quantify it into a similarity metric in order to be usable. To do this, I selected all of the features that had a defined value for all possible language pairs and then converted the information to numeric form. And then I used this information to calculate a similarity between all possible language pairs. I used datasets from 3 different language families and a total of 8 different languages. However, due to the scarcity of available cyberbullying datasets, I had to expand the scope to include any kind of abusive language. Looking at the results, although not the main point of this study, the cross-lingual transfer scores are considerably high, only around 10 to 20% behind the monolingual scores, even though no data was used from the target language. After calculating a correlation with linguistic similarity, you can see that there is a moderate correlation for both XLM Roberta and multilingual BERT with the WALS and e-linguistics metrics, but no correlation with EasyGlot. Maybe this could mean that lexical features alone are not enough to determine the similarity of languages. This also means that EasyGlot cannot be used for transfer language selection. But as there is a correlation between linguistic similarity and the cross-lingual transfer performance for this task, it is possible to choose an optimal transfer language by comparing the similarity of the languages, at least by using the e-linguistics and WALS metrics instead of relying on intuition. Furthermore, the method could have potential as a general method also for other natural language processing tasks. So to show the applicability of the method, I used 3 other tasks: sentiment analysis, named entity recognition, and dependency parsing. For sentiment analysis, the correlation dropped drastically for WALS and e-linguistics with XLM Roberta compared to the abusive language detection task, while EasyGlot showed a moderate correlation. A multilingual BERT had a moderate correlation with all of the metrics. The increase in the correlation of EasyGlot could be explained by sentiment analysis being more of a keyword-based task, which means the lexical features would be more important here. The reason behind the low correlation with XLM Roberta could be due to the task just being too simple, as it only requires classification as positive or negative. This also aligns with the results from previous experiments with feature density regarding the simplicity of this task. As you can see, it doesn't really matter what language you use as the transfer source, as the results are high anyways. This also, however, shows that it could be possible to achieve at least close to state-of-the-art results with multilingual transformer models in a zero-shot cross-lingual setting. Named entity recognition yielded similar results to abusive language identification. With the dependency parsing task, the results are going to a similar direction, but the correlation is stronger. As the correlation is stronger with a task that requires the understanding of syntax and grammar, this could support studies showing that transformer models can learn grammar without any explicit information, and also that cross-lingual transfer takes advantage of similarities in language structures. Looking at the results, there is a correlation between the proposed linguistic similarity metrics and cross-lingual transfer performance for all of the tasks. This means that it is possible to choose an optimal transfer language by comparing the similarity of the languages by using similarity metrics instead of relying on intuition. But which metric is the best to use? And even though having the highest correlation, the e-linguistics metric has its weaknesses due to only being based on a single aspect of language. Here you can see that e-linguistics shows Japanese being very distant from Korean, at the same level as Polish and Russian, with Korean being seemingly closer to Croatian than to Japanese, which is not true from a linguistic point of view. As the distance between the languages increases, there tends to be accidental similarities introduced to the consonant comparisons, making the e-linguistics metric more unreliable as the languages become more distant. The WALS metric, on the other hand, is obviously more robust to errors like this, thanks to being based on multiple features. So, zero-shot cross-lingual transfer can yield good results for multiple natural language processing tasks, possibly even rivaling those of monolingual settings. And most importantly, linguistic similarity metrics can be used to find an optimal transfer language. Also, I successfully quantified the WALS into an effective linguistic similarity metric. Ultimately, this makes it possible to develop detection systems despite the lack of data. And lastly, conclusions and further research directions. I aim to improve cyberbullying detection by hastening model development and by reducing computational costs and by enabling the development of detection systems when lacking data. For this, I used feature density to roughly estimate classifier performance and to reduce the number of required experiment iterations for cyberbullying detection. I also propose the use of linguistic preprocessings which improve classifier performance, creating better methods for detecting bullying. I also demonstrated the potential of zero-shot cross-lingual transfer, showing that using a language other than the target can yield good results. And lastly, I used linguistic similarity to find an optimal transfer language for many natural language processing tasks, including abusive language detection. Thus, this research helps in reducing the human effort needed to detect cyberbullying and hastens model development. In the future, I need to confirm the effectiveness of feature density also with other natural language processing tasks. Also, if transformer models can understand grammar, maybe adding grammatical information, for example, by applying the linguistic preprocessing methods discussed in this research to the transformer models' pre-training phase could improve their performance. Also, in order to find out what types of features are important for transfer learning to succeed, I need to group the linguistic features presented in WALS to different linguistic groups and analyze them in more detail. Thank you very much for listening.